Assalamu alaikum. So today we'll discuss the DC machine modeling. Now, as any machine, the DC machine consists of two parts, the stator and the rotor. So here I will plot a simple DC machine, and this is the stator, which is the stationary part of the machine. And let's assume it has two poles. And we're having windings fixed or placed on the pole. And let's assume that this is the sense of the current. Here is out, here is in, here is out, here is in. So according to the right hand rule, this will be the direction of the flux. So this is the flux axis, or sometimes we call it the field axis. And remember, all the time we are calling the field axis the direct axis. So this is the direct axis, or for short it's the D axis. And we're having the rotor. Now let's assume in the rotor there is winding, and the sense of the current that here is in, and in this side it's out. So again, according to the right hand rule, this will be the direction of the induced EMF. Now in the DC machine, we are using brushes, and also in the DC machine we're having a commutator. And let's assume that this commutator is simple commutator. It only consists of two segments, and according to the sense of the current here, this will be the direction of the induced voltage. So this is the direction of the induced voltage, or simply this is the quadrature axis. So this is the quadrature axis, or simply it's the Q axis. So now we're having the stator here, and we're having the rotor here. Now, while the rotor is rotating, still the axis, the D axis, is pointing toward this point all the time. And because of the using of the brushes, all the time the induced voltage is pointing toward this axis. So this is the brush. And we can place the brushes such that the angle between the D and the Q axis all the time is fixed to be pi/2. So simply this means that the DC machine is actually a 2-ax machine, two orthogonal ax machine. So it's simply, virtually, we can see it as a machine in the EQD reference frame. So this is what we call it, the simple two-pole direct current machine. Now, the first question, why we are needing the brushes and the commutators here? Simply, we can understand that from the first principle of electrical machine, if I need to generate a motion, I need a field and I need a current passing through that field. So according to the left-hand rule, a force will be generated. So here I will tell you the right-hand rule. If the field is in the direction of the pointer finger and the current in the direction of the middle finger, then the thumb will be pointing toward the force. So simply, this is the direction of the field, and this is the direction of the current. So this will be the direction of the force, and this is what we call it the left-hand rule. So this is the so now let's discuss why we need the brushes and the commutator. So simply, in general, if I have a simple coil, let's assume that I have one turns coil, and this is the, let's say, the coil, and here I'm connecting it to an external circuit, and let's assume this is the configuration of the, or the direction of the supply connected, here plus and minus. So the current will flow in this direction, and let's assume that this is the direction of the field. So this is the north, and this is the south. Now, according to the right hand rule, where the thumb is pointing, where the pointing finger is pointing toward the flux, and the middle finger is pointing toward the current, so the thumb will be pointing toward the force, and in this case this will be the direction of the force, and in the same principle this will be the direction of the force. So this means that a torque will be generated, forcing the rotor to rotate in the clockwise direction. So this is the clockwise direction, or the clockwise rotation. Now let's assume that we are achieving half revolution, or half cycle. So simply, this is terminal, let's say 1, and this will be terminal 2. So we will end up with the following scenario. And here is our supply. Now here will be the plus, here the minus. So the current will be in the opposite direction, and we are not changing the field. Direction of the field is not changed. So this is the north, this is the south. So now according to the left hand rule, a force will be generated in the opposite direction, and the machine will rotate in the counterclockwise direction. So simply, we need to maintain the same polarity of the current under the field ball in order to achieve a unidirectional torque and rotation. And this can be achieved using the commutator and the brushes. So simply, here we're having a simple commutator. Let's assume it only consists of 2 segments. And there will be some insulation between the segment. And here we have brushes. The brushes in order to allow the rotor to rotate and in order to allow connection to an external circuit. So let's assume this is the rotor, and in the rotor let's assume we're having 2 or 1 coil for simplicity, and let's assume here the sense of the current is in and here the sense of the current is out. So this terminal is connected to this segment and this terminal is connected to this segment, and the brushes is connected to an external circuit. So this will be the plus and the minus, and this is the VA, let's say. So in this case, while the rotor is rotating, the direction of the current will be maintained under the field ball. So in this case, we can achieve a unidirectional torque and a rotation. Now, in general, for the machine, we are calling stator and rotor. In the DC machine, the rotor is called the armature. Why? Because the induced voltage are induced in the rotor. So simply, the induced voltage which for short we call it EMF is induced in the rotor. So that's why we are calling the rotor the armature. While if we recall in the AC machine, either induction or synchronous, the place where the voltage is induced is the stator. So simply in the 3-phase synchronous machine or induction machine, the stator is the armature. So simply the armature is related to the place where the EMF is induced. And in the DC machine, the field windings are placed on the stator. So this actually we call it the commutator, which is actually a mechanical rectifier. Why we call it mechanical rectifier? Because the induced EMF is alternating, but because of the brushes and the signals, it will act as a rectifier, so the voltage here will become unidirectional or a DC. So the commutator with the brushes is acting as plus the brushes is acting as a mechanical rectifier. So now we need to discuss the modeling of the DC machine. Now, because of the configuration and because of our selection of the brushes, of course, sometimes we can shift the axis of the brushes, but simply let's discuss the simple case where the brushes is placed such that the angle between the direct axis and the quadrature axis is 90 degrees. So simply this means that we're having a machine in the QD reference frame. So we can use our knowledge from the QD reference frame in order to generate the mathematical model. So here we can say this is the brushes. This is the coil in the direction of the Q, and here we're having another coil for the field in the direction of the D. So this is the DS, and this is the QR. So simply, if we discuss the filming configuration, here is plus minus VDS. Here a current will flow, which is the IDS. This is a coil which has inductance LDS and the resistance RDS. The same thing here, plus minus VQR. A current will flow, which is the IQR. The same thing here, this coil has inductance, which is the LQR, and has a resistance, which is the RQR. And let's assume we're having a mutual inductance between them, which is, for short, we call it M. So this means that the machine is already ready in order to use our voltage equation in the DQ reference frame. Now, if you notice here, we don't have any coil in the QS or any coil in the DR. So simply this means that we have the following condition, that any function in the QS will equal to 0, which means that the current IQS is 0, the voltage in the direction of the QS equals 0. Why? Because we don't have any coil there. And also FDR equal to 0. Why? Because we don't have any coil in the rotor in the direction of the DR. We're only having two coils, one in the direction of the D and one DS, and the other one in the direction of the QR. So if we recall now, the voltage equation in the QD reference frame in matrix form, which we can write here, the voltage equation in the QD reference frame, and we will use the station reference frame. So here we having VDS. Here we will have VQS. Here we will have VDR. Now I'm writing the general voltage equation. After that, I will eliminate the unneeded terms, which is the VQS and VDR. And this will be the VQR. This will equal to the matrix here multiplied by IDS multiplied by IQS multiplied by IDR multiplied by IQR. Now let's organize it here. Now the first term here will be the RDS plus LDS d by dt. Here we have 0. Here we have the MD d by dt, and here we have 0. Here we have 0 RQS plus LQS d by dt. Here we have 0. Here we have MQ d by dt. Here we having MD d by dt minus omega r MQ. Here R dr plus L dr d by dt. Here is minus omega r L QR. Here we have omega r MD MQ d by dt omega r L dr, and here we're having R Q R plus L Q R d by dt. Now, in the DC machine, as we recording, as we stated here, in the DC machine, we don't have any coils placed in the direction of the, or along the QS and the DR, which means that I need to eliminate the second equation, the second line, and the third line from the matrix. So for DC machine, any variable or any function in the direction of QS equal to 0, and any function in the direction of the DR is equal to 0. So simply we only have two coils, one in the direction of the D S and the second one in the direction of the QR. So the voltage equation now would be reduced to VDS, VQS, QR, which will equal to R ds plus L ds d by dt, the first term here, multiplied by IDS. Then I will take this one, okay, this will be 0 here. Zero, and here we're having the I ds, and here we have the IQR. Now BQR will equal omega R MD, the first component here, multiplied by the current, and I need to take the last one here, which is the R QR plus L QR d by dt. Now, you know that if we have the voltage equation in the QD reference frame, we can find the torque. We can find the expression of the torque from the power balance, So, and here, because we are not using a transformation, an actual transformation, there's no be a factor 3/2. So simply the power in will equal the I Q D transpose multiplied by V Q D, which will equal to R ds I ds square plus R QR I QR square plus L ds I ds d by dt of I ds plus L QR I QR plus d by dt of I QR plus omega R M d I ds I QR. And simply here you can say that this is the input power or the total power, and those two terms are the ohmic losses, and the other two terms here those are the rate of the change in the field energy and finally we'll end up with the developed power. Those are the developed power. So we can take here the developed power, the power developed, which equal, it was equal omega R md, so omega R md IDS IQR. Now we know that the torque TE is equal the power developed over omega r mechanical, and simply we're having a relation between the mechanical speed and the electrical speed. They are related by the number of the poles over 2. So omega r will equal P over 2 omega r mechanical. So this is the mechanical speed. And this is the electrical speed. Now, by the mechanical speed is the actual speed, the shaft speed, the speed that we can see. The electrical speed is the speed of the electrical signal. So, TE will equal to P over 2 MD IQR IDS. Now, in the separately excited DC machine, this is actually a separately excited DC machine. Why? Because the armature and the field are separated. So here we can say that IA is equal IQR and IF is equal FIDS. So simply for separately excited DC machine, we have the IA by definition is the IQR and the IF is by definition the IDS. So if we need to write the voltage equation in the machine variable, which is the armature variable and the field variable, simply we will substitute instead of the DSF and instead of the QR the A. So this means that VA will equal to RA IA plus LA D IA by dt plus certain inductance, which is the LAF, the mutual inductance between the armature and the field, which is the MD here, multiplied by omega R IF, and VF will equal RF IF plus LF DIF by dt. Now, this term actually is the back EMF. Which we call it EA. So, EA is proportional with omega R if the field is fixed, if IF is constant. And finally, in order to finish the modeling, we need the mechanical equation of motion. which is the J d omega Rm by dt plus b omega Rm must equal the summation of the torque Te minus TL. And this is the load torque. And this is the electromechanical torque, Te, which is already we found to be Te equal to P over 2 md IQR IDS. So it will be P over 2 LAF IA IF. Now in the separately excited, IF can be fixed to be constant. So similarly TE would be proportional with IA, so it can be written as TE is equal to certain KT multiplied by IA. Now, if we do so, we have those two equations. This system will become linear if the IF is constant. And we will end up for constant flux or what we call it the armature control we can have VA equal to RA IA plus LA DIA by dt plus EA, where EA is equal certain constant K, let's say Ka multiplied by omega R. So this will be a linear control system, so we can use all our knowledge from the linear control theory in order to design it. Now, this is not the topic of this lecture. This lecture is for the modeling. So let's see how we can model the series machine, for example, or the shunt machine, or the compound machine. Now, according to the configuration of the coils, we can have different types of the machine. So the first one here we discussed is the separately excited. So let's assume that we're having the following configuration. So here will be plus minus V ds. This will be the I ds. And here plus minus V QR. Here a current will flow, which is the I QR. And this is what we call it the separately excited DC machine. So here IA will equal to IQR, IF will equal to IDS, VA will equal VQR, and VF will equal VDS. Now, if we connect the two coils in parallel, now this will be the total current. So here we're having the plus minus V terminal. This will be the plus minus V ds. This will be the I ds plus minus the V QR, and this will be the I QR. Now, this is actually the shunt connected DC machine. As we call it, shunt connected DC machine. Now, in the shunt connected DC machine, the I total, which is here, according to Kirchhoff current law, the I total will equal IQR plus IDS, and V total will equal VQR, which will equal VDS, which will equal VA, which will equal VF. Now, we can discuss also what about if the feed in series with the armature. So this will be the V terminal, this will be the I terminal, plus minus V ds, this will be the I ds, plus minus VQR, and this will be the IQR. Now here in the series connected, the I total will equal the IQR will equal the I terminal, and V total will equal VDS plus VQR, which will equal VA plus VF. This is the series connected DC machine. Now, if you notice here, we have two types of the field winding. One is the shunt, and one is the series. This is the shunt, and this is the series. Physically, they are not the same winding. Why? Because the series winding is connected in series. So simply, logically, the resistance of the winding must be small in order to avoid the losses. Remember that sometimes the current in the armature will be very high. So simply, if the resistance of the coil will be high, simply this means that a huge losses will be dissipated across the field terminal, and this is not applicable. So simply in the series field windings, in general the resistance is very small, while the shunt winding the resistance is very high. So simply if you have a machine and you don't know that the coils or the terminals are series or shunt, simply do the DC test or measure the resistance, and if the resistance is small, then this is the field, the series field, and if the resistance is high, this is the shunt field. So sometimes we can combine the shunt field and the series field in order to achieve extra benefit. So according to the connection, we have either a long shunt compound or a short shunt compound. Here I will draw it for you. And I will do the 2 in 1. So this is the armature, and here we're having 2 coils. So according to the connection, now let's do the first connection here, and this is the series. Let's assume this the first one is the series. So here we're having the series in series coil in series with the armature, and now we will connecting the shunting or in parallel with the series and the armature, and this is called long shunt compound. So this will be plus minus, plus minus. Here we have 2 coils in the DX. So this will be the VDS1 and this will be the VDS2. And here I will use the 1 for the series and the 2 for the shunt. So here we can write 1 is go for the series and 2 will go for the shunt. So here we have plus minus B terminal here, and here we have plus minus BQR. Now, what about the short shunt compound? Here, the shunt is connected directly in parallel with or connected or shunting only the armature. So we will have something like that. And here we'll have the shunt plus minus V ds2. Here we are having plus minus V ds1 plus minus V terminal. Here we'll have plus the minus the VQR. Now if you notice here, I switched the place of the coil in order to get a, let's say, an organized plot. Now this is called the short compound. This is the short shunt compound. Now already we did the mathematical model for the separately excited. I will pick one from those, so I will use the series, and please try to find the model for the shunt, the model for the long compound, the model for the short compound, in the same sense that we did for the separately excited and now for the series connected. Now in the series connected, if you notice here, for the series connected, we're having that I terminal, which will equal IA, which will equal IF, is equal IDS, which will equal the IQR. Yep. The current is passing the field and the armature are the same, and V terminal will equal VDS plus VQR. So simply, in order to find the voltage equation, we will go to the DQ voltage we already have, and I will add VDS and VQR. Then I will substitute instead of the DS by IT and the QR by the IT. So if we do so, we will end up with VT equal to R ds I ds plus L ds d I ds by dt plus M d omega r. The omega r was multiplied by IDS. IDS plus RQR IQR plus LQR DIQR by dt. So now if we use the following notation, we'll end up with VT is equal to RF plus RA multiplied by I total plus MAF or LAF. Let's use LAF. LAF omega R IT plus LF plus LA DIT by dt. Now again, if we need to find the torque, I will multiply by IT. If we do So we'll have VT IT, which is the total power. Then we have here RF plus RA IT square, which is the ohmic losses. And here we'll have the LF plus LA IT dIT by dt, which is the rate of the change in the field energy. And finally here we're having the developed power, which is the LAF omega R I T square. And from here we can calculate the torque. So TE will equal P over 2 in order to convert the mechanical to electrical speed, and LAF IF, which means that the torque in the series connected machine is proportional to IT square. So now we did the mathematical model for the separately excited and for the shunts. What I'm asking you to do is to find the mathematical model for the shunt connected DC machine, and for the long shunt compound, and for the short shunt compound. Now, and this will be left for you. So this will be the first part of the lecture. Now we will continue with the second part of the lecture.